I don't see any examples. Okay, I just know I guess I conclude there too. So it's my pleasure to introduce again as Marklof to the second lecture on applications of rigidity.
Okay, thank you. So yesterday I introduced you to what measure rigidity is, and I gave you a whole zoo of examples, mainly number theory, but also some examples that were motivated by quantum chaos. So this lecture today will deal with an application to an old problem in statistical mechanics, and even though I'll still just be able to scratch the surface on how we apply these techniques, but I hope I'll give you a good understanding on how we can solve this problem by translating it into a problem of closed homogeneous spaces. So this is the Lorentz gas, and the motivation goes back to Boltzmann's revolutionary ideas. So Boltzmann wanted to derive, for example, the laws of thermodynamics from the underlying microscopic laws of nature, in this case, Newton's laws of motion, for instance. Today you could also say, oh, we'd like to derive everything from quantum mechanics. But here we'll stick exactly with Boltzmann's concept. And using his ideas, and one thing I want to emphasize, these were really revolutionary ideas, Boltzmann and Maxwell in those days, because at that time, even the notion that matter should consist of molecules and so on was very controversial. So many people would ridicule him for these ideas. So the program that he developed to actually try to derive macroscopic transport equations from the Newtonian dynamics was really very revolutionary. And of course, in his work, he derived heuristically the nonlinear Boltzmann equation, which still today is an unsolved problem. And the main idea of Boltzmann was to use the, if you like, if we would say today, the hyperbolicity of the underlying microscopic dynamics of our particle gas. So Boltzmann would model the molecules just by hard spheres that collide with each other. And as you can see in this dynamics, here we have two such spheres. You have a sensitivity on changing your initial condition. So once you change the trajectory of your sphere slightly, the outgoing angle will change by double the amount. That just follows from the convexity of the scatterer. And so if you have n collisions, your error will basically grow like 2 to the n. And that introduces hyperbolicity. And Boltzmann's idea was to say, well, I'll just assume that consecutive collisions are independent, and a few other things, and then he got his famous linear Boltzmann equation. So as I said, even today we only understand the rigorous derivation of the Boltzmann equation for short times only. That's famous work due to Oscar Langford.
But he has to make a big assumption. He also has to make a big assumption.
No, it's just short times, yeah. Very short times. So the time has to be shorter than the mean collision time. Beyond that, we can't say anything. There have been some recent papers that, again, investigate Boltzmann's work, but to the best of my knowledge, this is really still the state of the art. And that's maybe surprising, right? That seems, again, a simple to formulate problem, and more than 100 years after Boltzmann and Maxwell will still can't answer this question. Now I'm going to talk about a much simpler model, and that's the Lorentz gas. So motivated by Boltzmann, Lorentz said, I'd like to model transport of electrons, say, in a metal. And so the way he modeled matter is simply by fixed scatterers, which we can still assume to be hard spheres. You could also put a potential in there and make it a little more realistic, but let's just assume these are, again, hard spheres. And then the particles that move through your metal or your crystal or whatever you like, are point particles that don't interact with each other. Okay, that's the big simplification over Boltzmann, but they only interact with the scatterers. So effectively, you can just look at one particle in your particle cloud and trace its dynamics. So using the same ideas as Boltzmann, Lorentz derived an equation, which I come to the next slide. Here's just, so on the previous slide I showed you a sort of random configuration of these scatterers, and on this slide I'm showing you a crystal-like configuration of scatterers. That's the famous periodic Lorentz gas. And again, here we're interested to trace a test particle that moves around this crystal. So, Lorentz's idea was to, as in the case of Boltzmann, study a kinetic limit where the size of the scatterer is very small compared to their average distance. That's a low density limit. And in this limit, you hope to recover macroscopic transport laws that explain the dynamics of a particle cloud. Now, how do we set this problem up mathematically? So rho will be the radius of our scatterer, and q and v, q will be the position of our particle, and v the velocity at some time t. And a simple scaling argument shows you that the time between collisions and the free path lengths between collisions should grow like rho to the minus d minus 1, this factor here. And this is the cross-section that each particle sees as you shoot off. Right? So there's a simple argument. This is a well-known calculation in statistical physics. And so if you want to now, and it makes sense, right? As your scatterers become smaller and smaller, you fly for a longer time. So now what you need to do to recover a good limit is to measure time and length in these units of the mean collision time and the mean free path length. So we rescale everything. Yeah? We rescale our time by this factor, and we also rescale our position coordinates by the same factor. And velocity we just keep as it is. Think of moving with unit speed. Okay, speed is preserved because our scattering process is elastic, so if we come in with speed 1, we'll exit with speed 1. So let's just restrict ourselves to velocities with absolute value 1. And so, now what we get here then, in the macroscopic coordinates, capital Q and capital V, we get a flow, which I call billiard flow, because essentially that's what you got, right? It's like a pinball machine, if you like, or you could also think of a billiard table, where you have heavy balls fixed and you're shooting on with one ball and try to see how it flows around. So that's a billiard flow. But unlike in dynamical systems, typical questions, is we're not fixing a system here. We're looking at a whole sequence of systems because rho tends to 0, okay? And we're trying to understand if there is a limit of this sequence of systems. How do we set this up? So here again is our billiard flow. And now we want to talk about an initial particle density that we propagate under this flow. So F here will be some initial particle density. That is some L1 function on our unit tangent bundle of our phase space. And we just propagate it in the usual way. So the density will be evolved by this linear operator, LT rho, which is just defined by this relation. And so what Lorentz suggested, following Boltzmann's ideas, is that in the limit we will have this linear Boltzmann equation in the limit when rho tends to 0. Okay. And if you think of the left-hand side, that's a so-called transport term. So if the left-hand side would be equal to 0, that would just be a free motion of the particle part. You can solve this equation. So if the particle doesn't hit anything, it goes from q to q plus dt, right? And so you can just plug this into the density up here, and you see that if you have this as your flow, just the free flow, it satisfies.
So the unknown is ft?
Unknown is ft, yeah. And the right-hand side corresponds exactly to the collision term, and it tells you that when the particle hits something, with a certain velocity, it will exit with another velocity v that is distributed exactly according to this differential cross-section of the single particle scattering process. Now, I don't want to define all this and set this up, so if you don't know what the...
Wait, q and v are also unknowns, right?
So, okay, we want to find the solution of this.
Yeah, what are the unknowns?
So, we want to find out what is f of t, what's the function. And q and v are the variables of this function.
It's giving you a distribution of position.
Exactly. Of your particle cloud. Think of a particle cloud at time t. Right? That's what you want to calculate, and it gives you the distribution in your phase space. Okay. So that's the classical linear Boltzmann equation. And this equation has seen many applications. For instance, neutron transport in matter, where the neutrons would be our small particles moving around in some fixed material, or radiative transfer, and many things like that. Now, of course, we asked, can we prove anything? Lorentz arguments were as heuristic as Boltzmann's. Big advantage, of course, of this equation, and I should highlight this, is that it's now linear. It's no longer a nonlinear equation like Boltzmann's original equation. And it took a few years and a few bright people to prove that Lorentz was right. But the crucial assumption was that your scatterers had to be randomly distributed. And randomly distributed, in Galawati's work, meant the centers of your scatterers had to be at the locations of the spatial Poisson point process. So, for those of you who don't know what a Poisson point process is, it's just a way of assigning a probability measure on an infinite point set in R2 in our case, or RD in arbitrary dimensions. And the Poisson process has a lot of nice properties. It's somehow the maximal random process that you can imagine. Okay. I don't want to say more here. Main point is these scatterer configurations had to be completely random. Important follow-up work by Spoon, and then Borghini, Bulnimovich, and Sinai proved that, in fact, not only for a random configuration, but for a generic realization of your random configuration, you converge to this linear Boltzmann equation. So then, the immediate question is, well, what happens if you don't have a completely random scatterer configuration? And of course, the extreme case that you can think about is a periodic crystal, right? In other words, a lattice. So you put all your scatterers on a Euclidean lattice. And in this case, and this is what this lecture is going to be about, in joint work with Andreas Strömbergsson from Uppsala University, we showed that again, if you ask, where does my initial particle cloud go after time t, where t is again measured in unit of the mean collision time, remember we had to rescale everything, and you take the limit, as the scatterers go to 0, do you see anything? Is there any dynamics that you get in the limit? And this theorem says that yes, there is a good limit, and the particle plot at time t converges weakly to some answer. So this is what I mean by weakly. It's just you take your particle cloud, you propagate it, and then you integrate it over some test set. So the left-hand side somehow gives you the probability that at time t, your particle is in some test set A. And the right-hand side is the limit as rho tends to 0. And it's given by a family of linear operators, LT.
What's LT rho?
LT rho is this thing up there. So LT rho is just the propagator that propagates your microscopic dynamics. Okay? And the amazing fact is that this family of limiting operators actually doesn't form a semigroup. And this is a bit funny. So when you look at your LT rho, that is a semigroup. And why is it a semigroup? Well, the microscopic dynamics is driven by your Hamiltonian flow, right? So if you propagate your particle density to time s, and then you take what you've got at time s and you propagate it again by time t, this must be the same thing as taking your initial particle density and propagating it to time s plus t. That's the semigroup property, right? Now this breaks down in this limit. You lose some information.
How is it possible? How?
I show you. Okay. So the reason for this is that you need to keep track in this limit. So some of you might have heard this. It also puzzled people a lot in Boltzmann's original work that sort of time invariance is lost, right? Entropy production, all of this. And so this is a phenomenon that also falls into this category. It sounds a bit funny, but the fact is that you're going into quite a singular limit. And now the resolution of this problem...
Before you change, the statement is just that there is a time evolution. The theory is there is a limiting time evolution as rho goes to 0. So that's the statement.
That's the statement.
It's not a semigroup.
Right.
And the statement that it's not a semigroup, that's an observation. Yeah.
So what this T of F on the right-hand side is a solution of the linear Boltzmann equation? No. So what is it?
If there would be a solution, it would be a semigroup.
Yes, so what is it?
I'll show you. Don't be so impatient. I'm trying to build up a bit of tension here.
Is there any failure you would observe it? If the limit exists, you would observe it.
If the limit exists, you could observe it, right? But we can describe what it is a little bit better, okay? Let me show you how this goes. So, we lose information. So the solution to this problem is to keep track of more variables as you pass to the limit rho to 0. And the variables that you need to keep track of is the time until you hit the next scatterer. So imagine you have this particle that's moving around. Okay? So this, you now want to record not only your position and velocity, which is enough to determine your flight trajectory until infinity. Hamiltonian dynamics only needs position and velocity, and you know you can solve all your equations. But you need to keep track of more. The time until you hit the next scatterer. This microscopically is a function of Q and V, of course, right? And the velocity after the next hit. So keep track of these variables in the limit. And now look at a density Ft that not only depends on Q, V, but also on psi and V plus. And then what we show, that this density converges weakly to the solution of this equation. And this equation is, if you like, a generalization of this linear Boltzmann equation. It looks a bit similar. On the left-hand side, it's again some linear transport term, and on the right-hand side is some variant of a collision integral. And this collision integral basically tells you that when you hit something, so remember, this is the time until the next hit. So if this time is 0, then we exactly have a collision. And this collision kernel here tells you the probability of hitting the next guy after time psi and scattering with velocity v plus. Okay, so this is the form of this equation.
So the rho P0 exists, you're proving it exists.
Rho of what?
This P0.
P0, it exists, yeah.
You're proving it exists.
Absolutely, yeah. So all of this, we all have description for all these things. But this is the new equation. And as I mentioned, we're particularly proud of this because physicists hadn't seen this before, and physicists didn't have an idea what form this transition kernel should take. So here's the equation again, and as I say, for our crystal, for our periodic scatter configuration, we have a particular formula for this. And I'll illustrate to you later how we get this. But in fact, if you have a random scatter configuration, you can also calculate a formula for this. It's quite easy. And this formula just looks like this. And this is related to the following fact. Imagine you have a random scatterer configuration. What you find is that the time between two collisions is actually follows an exponential distribution. We've seen this yesterday when I was talking about gaps in the Poisson process, which is exponentially distributed. So also here, the time between collisions is exponentially distributed. It's the most natural thing that you can expect for a positive random number in such a context. Okay? So that's why, so remember, this is somehow giving you the probability of hitting the next guy off at time psi and exiting with velocity v plus. And here again we have the differential cross-section, which gives us the relation between the previous velocity and the exit velocity. And if you put this particular function in here, and you make this ansatz, you separate variables and you get the linear Boltzmann equation. So from this point of view, actually our equation here is the more general equation. And you can say, well, great, so now I have a more fundamental equation that describes not only the random scatterer configuration, but also the periodic one. And what I'm working on right now is trying to understand what happens for other scatterer configuration, like quasi-crystals and other random processes. But I'm not going to go into this. I'm just going to show you why this is so for the periodic scatterer configuration.
What's sigma?
Sigma is this differential cross-section. Do you want me to explain to you what this is?
Oh, okay, the differential cross-section.
Yeah, that's what it is. Good. So the key theorem, actually, the way we prove such an equation is we actually show that there is a random flight process that describes our particle trajectory. So, microscopically, we look at some initial condition here, so we shoot up from this point, in a random direction. Right, so you think of your particle cloud. And one way of reformulating it, instead of thinking of a particle cloud, is to think of a particle in your cloud that has a random position and a random velocity. So we shoot this off, and so you get a random trajectory, right? Now we take rho to 0, and what you'd like is that in the limit, you get a random flight process that describes where your random trajectory converges to.
You have a random what process?
Random flight process.
A random flight.
I'm calling it a random flight process because the way we scale things is our mean collision time or mean free path length is sort of fixed, right, in those units. So you always fly for some time, for some random time, then you hit something, then you go in another direction, fly again for some time, and so this is why I'm calling this a random flight process. So we want to understand, in other words, the joint distribution of all those legs of our journey. Does that have a limit? And this is what this theorem that's on the next slide is telling you. And don't look at it, but that's the key theorem. It just tells you, look at the first n legs of our journey. That will have a limiting distribution. And in fact, that probability density that describes our limiting distribution factors in a very nice way. And this factorization means that the process that generates in the limit the length of our journey is a Markov process with memory 2. In order to understand the distribution of the jth guy, you only need to know the distribution of the previous 2. That's something we prove, and it's hard to tell you why it is so, why it is Markov memory 2, and so on and so on. You shake your head. It is. I do have, but it would take me an hour to explain it to you.
What is that tree? Is that tree in the first lecture?
This tree? Which tree? Ah, here? This tree?
Yeah.
That is the number of legs that we're looking at. It's just the formula doesn't look, it looks a bit different when n is, you see I need a sum there. So if it's not 3, you just get this term. I think that's why I put it down myself. Okay, so this is the key theorem, and once you have this, then you flow with speed 1 along your path, your random path, and then you just apply actually Kolmogorov's old observation that then the solution, so the flow along this path satisfies the equation that I wrote down on the previous slide, because that's just the Kolmogorov backward equation of this random flow. This is also called Fokker-Planck Kolmogorov equation. But don't worry about it, okay? I just want to show you this theorem to show you what we proved, how we got there. That's the main result. But what I'm going to do now is explain to you what the key step in our proof is. And what I want to do is I want to just ask the first question in this. And that is, you're a particle, you sit somewhere in your Euclidean lattice, you're shooting off in a random direction. When do you hit the first scatter? That's the first question, right? The first leg of our journey. So that's what I'm going to discuss. If you want to prove the whole theorem, then you need to worry about where you hit the scatter, where you fly afterwards, and what you hit next, and so on. But this is going to be more complicated, but it's just technical stuff. The key idea you'll already see in the first slide. Okay, and the first slide has a long history. People looked at this problem. One of the first is Polya, who wrote a beautiful paper on visibility in a forest. In fact, the paper was called Number Theoretic and Probabilistic Considerations of Visibility in a Forest, because he imagined his forest to be either all trees randomly distributed or all trees on a perfect grid. And he asked, how far can you look? Right? And if you think about that, it's exactly our problem if you assume that your tree trunks are perfectly circular. And they should be pretty thin as well, in our particular limit. Now in dimension 2, the distribution of the 3 path lengths, so that's really the question of shooting off in a random direction. What's the probability that you hit your first scatterer or your first tree after time t? Was answered by Boca and Zayarescu and their co-workers using methods from number theory, continued fractions. In higher dimensions, the results were much scarcer. The most important results are due to Bourgain, Goltze, and Vanberg, who proved that the distribution of 3 path lengths has to have a certain heavy tail. They had upper and lower bounds for these. And so this was
law decay. There's a power law.
Power law decay, exactly. That was the amazing observation. And then eventually we settled this question in joint work with Strömberg, where we proved that in any dimension the distribution of 3 path lengths exists, and we could also actually show that this power law tail is actually the asymptotic tail, not just upper and lower bounds with an explicit formula for the constant. Okay, so how does this work? Here is Polya's forest. Okay, I was traveling through, I've read Polya's paper, and I thought, well, great assumption that trees should be randomly distributed. don't know if the Poisson distribution is an adequate description, but I've never seen a periodic tree. Of course, you think of an orchard or something like that, but a periodic tree I've never seen. So I was traveling through Italy in the train, and then this thing came by me. I couldn't believe my eyes. I thought I was hallucinating. So I got, so my father-in-law lives nearby, so I said, we have to go there. And he said, well, they're everywhere here. So this is some paper production, I guess, or something. I don't know. Or matchsticks. I have no idea. But they're actually on a perfect grid. So you see the rational directions if you stand in there. They're really pretty precisely done. You see a few defects here. There's one tree missing, but I guess nature also wants to have an impact. So here's the theorem that I want to explain. So this is a special case of the theorem I showed you before, where we have the whole journey. This is just when do we hit for the first time. And, okay, so tau 1 will be the free path lengths for some initial condition. So we're sitting at some point Q, and we fix that, and we're shooting off in a random direction, v, with unit speed, okay? Now what does random mean? Well, we'll fix some probability measure. Just take the uniform measure on the sphere. So just shoot in every direction with the same probability. This theorem is already hard enough, okay? We of course want to put some weights on, we want to choose other measures on the space of directions, but just take one to be the uniform Lebesgue measure on the sphere, and it's already hard enough for the problem. And so this theorem says, well, there is a limiting distribution, and the limiting distribution depends, for example, on whether your initial point is a lattice point, say the origin, or if it's not a lattice point, if it's a generic point. And by generic, I just mean here, I don't want it to be a rational multiple of a lattice point. You get two different answers for this limiting distribution. Okay, so that's the probability that we hit after time psi. And psi is measured again in these units of the mean free path length. Remember, we should rescale everything by this factor, because tau 1 is growing exactly the inverse of this rate. So, here's the theorem, and I'm going to show you, see in gray here, I'm hiding something, because before I do this, I want to show you how these distributions look like. So here is the density of that probability. So f psi is a distribution function, probability distribution function, and phi here is the density. So this is the answer when you shoot it from a generic point, and you see this tail, which turns out to be algebraic. And when you shoot up from the center of a lattice point, you get a compact support distribution, which follows from some standard effects, actually, in the geometry of numbers. In Costi could have told you that. But this is really the surprising thing. When you sit on some generic point and you shoot off, you get this distribution. And compare this with what happens for a random scatterer configuration, where your distribution is an exponential distribution. Right. And here are the tails, and you see we get a precise constant from. Goes like psi to the -2. It's amazing because this thing doesn't even have an expectation value when you shoot off from a generic point. While the other one has compact support, as I just described. We also know what happens near 0.
Zeta was 7 centimeter.
Zeta of d, the Riemann-Zeta function. Exactly. So now some people get excited, but it's unfortunately not at the right place. This is very simple. 1 over zeta d is just the relative density of primitive lattice points. And when you look at the expansion at small psi, it actually is the same as what you would have if it would be a random scatterer configuration, where it's e to the minus psi, so if you expand that, you get some constant. Exactly this constant, but corrected by this factor. And why is this? 1 over zeta d is the relative density of primitive lattice points in all lattice points. So what does primitive mean? If you sit on a lattice point, it's exactly those guys that you can see. Yeah? can only see the primitive lattice points because all the other ones are hidden behind. And this is why you get this factor here, because your particle, if it's coming from a scatterer, only sees the visible guys. So that's my explanation why somehow this is the correcting factor that it gives. Anyway, we can prove it, so we don't need a heuristic factor. So let me now show you what the actual answer is, from which we can derive all these properties.
But that's only sort of true if you have a positive rho.
Yeah, but now rho is 0. This is the limit. Limits, yeah. So this really only emerges in the limit. Now, very good. So the probability that I just showed you some plots on and some asymptotic tails is actually described, so if we shoot a from a lattice point, by the probability that a random lattice L tilde avoids the cylinder that I've written down here. It's a cylinder of length psi. It's a thing like this. So this is length psi, and the radius here is 1, I think. Yeah? And if you shoot it from a generic point, that is given by the probability that a random affine lattice avoids the cylinder, the same cylinder. Now you're all experts already in the space of lattices and so on, but let me just remind you what all these words mean. What is a random lattice? So this slide we had yesterday. Take a Euclidean lattice of covolume 1. You can describe the space of all Euclidean lattices with covolume 1. You can parameterize it by SLDR modulo SLDZ. And we can define probability measure on this space, which then assigns a certain weighting to each lattice that comes up, right? So that means we have a notion of a random lattice. You just pick a random lattice with respect to that probability measure. So the answer says that the distribution is given in this way. And I'm going to show you why this is so, okay? So don't get anxious. I'll explain to you why this is. And similarly, when we shoot up from a generic point, because now we basically, relative to where we are, we need to shift our lattice. So it makes somehow sense that the limiting distribution is given by a random affine lattice. You find exactly the same way. So now you take SLDR and the group of all translations of RD, and you take a semi-direct product, which is defined in this way. Let me just remind you that I'm always thinking of all vectors being row vectors, and so I'm multiplying notices from the right here. And so again, this will be our Lie group, and our lattice in this Lie group, the discrete subgroup, will be SLDZ times ZD, which preserves our lattice, ZD. And so then the limiting distribution is simply the probability with respect to our R measure that a random point in our space of random affine lattices doesn't intersect the cylinder. And why is this? So let me now try to explain to you why this is. I'm going to restrict myself to the case when our initial lattice is just a cubic lattice and the point we're shooting from is a lattice point, so the origin point. So here's our initial point, and we're shooting in this direction, and we're asking, when do we hit the first guy? Or in other words, what's the probability that we don't hit the first scatterer within time psi? So this means we want to find the measure of directions for which this ray doesn't intersect any of those disks. Right? So this is a bad example. Okay, so you need to turn this thing, and whenever it doesn't intersect any disk, then we're fine. That's what I just said. Okay. Written down. And now, this problem is almost the same as requiring that there is no lattice point in this particular cylinder with the same length as our initial ray, and radius rho. You can think about this a little bit and convince yourself. It's only approximately true because this cylinder should really have a spherical cap here and there, and then it will be completely true. Okay? But our cylinder is very, very long, and the probability that there is a point in here, this little spherical tiny cap, is very small. That we can show. Okay? So you can just forget about that. So let's just assume that you accept that the probability that we want to calculate is given by the measure of directions for which this cylinder doesn't intersect any lattice point. Now the problem here is that this is a very thin, very long cylinder. So what do? And now comes the key step in what we do. And you'll see it's so trivial, and it's funny that no one else had designed it before, okay? Well, we just rotate the whole thing, number one. And then we apply a diagonal matrix to push the whole picture together, okay? So I've rotated the whole image, and now I've pushed it together. So what have I gained? Well, my cylinder is no longer thin and long. It's nicely proportioned. And it doesn't depend on rho anymore. Okay? It's now a fixed object. Of course, the price that I've paid is that my lattice is now a function of velocity and rho. So, what have we got? We've got a random lattice now. Here it is. Okay, down here. We've rotated our lattice, and then we sort of dilated it with this diagonal matrix. Maybe that was a little fast. The matrix is here. Right, so the one direction, the long direction, I push together, and the thin directions, which are in this plane, I expand. Okay? And now notice this is a matrix with determinant 1. Rotation, of course, is determinant 1, so both of these guys are in SL2R. So, we're now asking the question whether this lattice intersects our fixed cylinder. And it's a random lattice, so we're asking what is the probability that this random lattice intersects the cylinder. We want that not to happen, so we want that this lattice doesn't intersect the cylinder. So it's a sequence of random lattices that shouldn't intersect the cylinder. And what this theorem here shows you is that this sequence of random lattices converges to a random lattice with respect to our measure. And for that, we use homogeneous flows. Okay? So let me step back a bit. What does this theorem say? So here we have a random lattice. We know that we can identify a lattice with a point in our homogeneous space. Space of lattices, I call it x1. So this guy is a point in x1. Okay? Now we rotate it by this matrix and we apply this translation. So this here, you can think of being parametrized by the sphere in our homogeneous space, and multiplying with this diagonal matrix you can think of as multiplying, acting by this one parameter subgroup here, just as we discussed yesterday. Okay? So you have this sphere, you push it with the diagonal subgroup, and what this theorem says is that if you integrate with any nice measure over the sphere, it becomes infradistributed in x1 with respect to our measure. Okay? Now, how do you use this theorem here to prove the distribution of the free path lengths? Well, this test function here you simply take to be the characteristic function of the condition that the lattice doesn't intersect the cylinder. That's a nice characteristic function. It's of course not a continuous function as I'm assuming here, this equidistribution statement, but you can apply some measure theoretic tricks to to show that because this characteristic function has boundary of measure 0, you can actually approximate it by continuous functions. Okay. And this theorem D that I just showed you is a consequence of the mixing property for this flow phi t. And as I said, that concludes the proof for the existence and the limiting formula for the three path lengths when we shoot off from a lattice point. Now, when you shoot off from another point, a generic point, then you need a stronger version, and that requires Ratner's measure classification theorem, in other words, measure rigidity.
So how difficult to prove mixing? How difficult to prove mixing?
It's a classic theorem. It follows from the old theorem by Moore. So that's well known. And let me just say one word. Why do we use Ratner here? Well, we use Ratner because we're integrating over the spheres, but you can show that spheres, when they become larger and larger, are getting close to horospheres. And horospheres are generated by unipotent orbits. So you can actually show that if there's a limit, remember my first proof of Waal's theorem, we'll just say, okay, let's assume there is a converging subsequence. We know it has to be invariant under unipotence. And so we can apply Ratner's theorem, which tells us what are the measures that are invariant under the unipotence. Then we'll look at all of them, and we'll find out exactly the ones that correspond to our limit. Okay, great. So that was the crystal, and I just had 2 slides of very recent work. I told you that I'm very interested now to understand what other scatterer configurations give you new answers. And so one thing is to look at quasi-crystals and other things, but a very obvious thing is what you could just do is you can take some union of 2 lattices. Okay? Just take a union of 2 lattices and make that your scatterer configuration. Now, don't read what's written there. It's a bit too much, I think, for this time of day. But if you assume that the 2 lattices are somehow incommensurable, that there is no, you don't want to take the identical lattice to get this result that I'm talking about. You can do it for an identical lattice, but the answer won't be so interesting. Take 2 lattices that are sheared against each other and rotated against each other in some generic way. What we can show then is that, again, the 3 path lengths exist. Well, we can show this for any union of any lattices, but the answer in this case is very nice. So you take n lattices that are pairwise incommensurable, and so your limiting path length distribution will be actually the product of the path lengths of each individual lattice. So the 2 decouple. And that, again, uses very heavily this theorem, Ratner's theory. So now we need to look at the nth power of our SLDRs and show that we're becoming some of our spheres becoming uniformly distributed in the nth power. And that's a very, very non-trivial statement. What it shows you is that actually in this way we can construct arbitrary polynomial decays, not just psi to the -2, but psi to the -n, where n can be any integer. Okay, so I hope this is just the corresponding equidistribution theorem that we are proving to use Ratner. So here you've got, again, your sphere that's appearing in n copies of your SLDR, but it's the same sphere everywhere. Right? So it's this d-dimensional sphere embedded in this nth power of SLDRs, and again pushed by just one diagonal flow that's embedded diagonally in your product. And Ratner shows us that this becomes uniformly distributed in the big space. It doesn't stay on some subspace. So I hope I've given you a little bit of an idea of what's going on here, right? So the key step is, again, the translation. And I hope I've convinced you that it's pretty simple. The idea of just saying, okay, rotating my lattice, pushing it together. That's how you create dynamics on the space of lattices. And you make sure that the set that you get then, your cylinder, is then a fixed set. That's really the key idea. And then, of course, you can do all this homogeneous flow dynamics, but that any expert could have done, okay, this last step. Key step was really to find the translation of the problem from the geometric question of the free path lengths to a question of the dynamics of the flow of homogeneous spaces. Okay, thank you.
More questions?
Where did you use the semi-group property here?
So, yeah, so the fact that it's not a semi-group, you have to prove, because it could just happen, right? That it is preserved. But we can show this, and it's a calculation we have to do. So, the way I think of it, in the sense that it doesn't surprise me so much anymore, is that I think of this Markov process with memory 2 generating the evolution of this density. So I'm just writing it down here, which had this additional 2 variables. And when you're interested in your original time evolution, you're going to have to project this down by integrating out these 2 variables. So this was the guy we were originally interested in. And I said, we can't generate that by a semi-group. So this is like a projection operator. And the right initial condition you have to choose for our equation is by taking your initial physical density that we wanted to start off with, and then you multiply a certain equilibrium state in the other 2 variables, psi u plus. So you take this as the initial data for this transport equation, then you evolve it, and then you project. And so now the semi-group property is lost because when you evolve to time t1, you project, and then the projection you lift up again into your higher dimensional space by multiplying with this function. These 2 things simply don't commute. That's how I explain. I don't know if it's satisfactory. Maybe you'd like to see something else, but the key point is that this Markov process that we get there has too much memory. And this is reflected in the fact that we need to. So if you have higher memory, you need to have a higher state space. And this space is described by these additional variables. So that's the best explanation I can give.
I have another question. In physics, you usually produce equations which predict the future in terms of the past, but here you're using the time to the next collision, which is thinking about the future as part of your data. Is that essential?
No, it's not essential. I think you could revert that. I haven't written it up.
Last collision? Could you use the time from the last collision?
I think what you would need to do. So you can run our equation into the past, and then turn everything around. Then you will get your description. So it would be possible. Yeah. It just came out this way, and I liked it. But one can do this certainly.
More questions?
Do you have a heuristic reason for the fact that the memory is larger than 1?
Yeah. So. This is the following. When you solve the whole problem, what you need to understand is, so you imagine you're following this particle and the neighborhood of this particle, and suppose it just hit something, and now you look at a particle beam that has hit the same scatterer. And it will take a long time until this particle beam will hit the next scatterer. So these particles will be almost parallel. So you have a particle beam coming into the scatterer that we and I have to zoom in because the microscopic dynamics, even though we look at this, will play a role here, unlike the random scattering configuration. So we're now going to hit the scatterer, with some distribution on what this is called the impact parameter, is where you hit the scatterer in the direction perpendicular to your incoming velocity. So these are all coming into the same velocity parallel. And then because the scatterer is convex, this will give you a distribution of the outgoing velocities. Right? So this one will go this way, this one will go this way, this one will go this way. So this will be, so if we call this V0, this will be the velocity V that I've been talking about. Okay? So now, let's turn this picture just to make it clear. So let's turn this, focus on this guy here. We're going out with a velocity V that is a random variable. There was a random variable here describing the cross-section of our incoming beam that will give you a probability density, a nice probability density on the V's. So think of V as now being random. And what you would like to understand then is that what is, so suppose we've just hit here and now we're flying in this velocity. When do you hit the next scatterer? And you also need to understand where you hit it. Because the scattering process, of course, depends on your impact parameter, right? So you need to know what is the new impact parameter that you're hitting over there as a function of this exit parameter and the velocity. And what we show, what we prove is that this probability exiting here and hitting here after time psi, well, with a right rescaling, will depend on the exit parameter, this guy here, will depend on where you're hitting, but it will be independent on the probability measure on the V's. That's why we're losing, that's why we get independence on some scale. But the fact that the transition probability depends on S and the impact parameter V, you can make a little calculation to show it, shows that you have this memory 2 effect. But not memory 3 because of this phenomenon that actually it doesn't depend, this probability doesn't depend on the distribution of the velocity. So it doesn't matter if you're shooting in a rational, near irrational, irrational direction, vertical, horizontal, doesn't matter. Because, well, that's what we prove, right? So that's the observation.
Any other questions? Alright, so before we finish, so let me just remind that the third lecture, this may cost tomorrow, it's 2:30 in this room. And now this evening we will have a dinner, so everybody who is interested just stay here and for a minute and let me know that. So if you would like to join us, and now let's